Right, just Miller, Rockstar Going Physics here. We are going to look at a couple problems involving projectile motion and solve some stuff out, make some connections, and then well, we'll do some more. So let's just begin. So projectile is always subject to a gravitational acceleration, constant velocity in the x direction. The acceleration in the y direction is negative g j hat. And that's what we've got going on for us. So here's the problem. Okay, so we've got ourselves a projectile or an object that is launched at 20 meters per second at an angle of 0 degrees with respect to the horizontal when it is initially 10 meters above ground level. And we want to know some things like how long is it in the air for, what's its displacement in the x direction, what's its overall displacement by the time it reaches the ground, what's its velocity as a direction of magnitude when it reaches the ground, stuff like that. So first off, let's draw a little picture just to get some general expectation of what we've got going on. And just have some model here so we can imagine that we're on top of a building or something like that, a cliff that is 10 meters above ground level. There it is, there's ground level right there. This would be the 0 meter mark, 0 meter ground level. And we're gonna go ahead and have some projectile that has some initial velocity of 20 meters per second at an angle of 0 degrees. So 0 degrees would just be that way, and we've got ourselves that V initial hat is equal to 20 meters per second at theta V initial is equal to, that's the magnitude, and the direction is 0 degrees with respect to the horizontal. So it's basically we throw it off completely horizontally, and we want to know how long is it in the air for. So let me move this over a little bit. 20 meters per second, how fast is that? Again, 1 meter per second is approximately 2.237 miles per hour. So we could get a pretty good estimate of what 20 meters per second is, multiply it by 2.2, and we've got ourselves, it's a little bit more than 44 miles an hour. So we take something, throw it off horizontally, 44 miles an hour, and what's it gonna do? Well, it's gonna start dropping to the ground, right? So we've got a little trajectory here that we could expect this object to undergo. So something like that. We just have to model it out. We really don't know how far away it strikes the ground. This is probably not completely accurate, but we still got an idea of what sort of quantities we've got here, right? So what do we have? Well, we can mark out some things, like there's a delta x, there is some delta y, you can draw that direction. Delta y is down, delta x is that way, and this is what we've got. So what do? We start looking at what's being asked. First question that's asked is, how long is this object in the air for? Total time. The air equals what? So, whenever we've got these types of problems, really the first thing that we want to do is think about breaking its motion down into x components and y components. So if we start looking at things like, hey, what's the initial velocity in the x direction versus the initial velocity in the y direction, we can start to make some correlations here. So first off, we've got that Vx initial is going to be equal to V initial times the cosine of theta V initial, which in this particular case would be 20 meters per second times the cosine of 0 degrees. Cosine of 0 is equal to 1, and we've got ourselves, hey, it's 20 meters per second. If we go ahead and do the y component, in general, we've got that the y component is the magnitude of the initial velocity times the sine of theta v initial, which would be 20 meters per second times the sine of 0 degrees. Sine of 0 is 0. Well, look at that. Well, that should stand to reason we're throwing it at an angle of 0 degrees. There is no y component. We're not throwing it up at all. We're not throwing it down at all. We're throwing it initially completely horizontal. So it only has an initial component of velocity in the x direction. No y component. So then, what else are we looking at here? Well, let's look at our equations that we've got. In general, we've got equations for the y direction. Let's say delta y is equal to -1/2 g t squared plus vyi times t. Vy final is equal to -gt plus vy initial, and vy final squared is equal to vy initial squared minus 2g delta y. And we've got the x direction. Delta x is equal to vx initial times t, and vx initial is equal to vx final is equal to constant because a sub x is equal to 0. No acceleration in the x direction. Really, all we need is this. We know it's a projectile. These two fall into place because of that. Anyways, this is what we've got to work with. Well, we want to figure out how long it's in the air for. So let's look at the simple expressions here right now and think about what do we know, what do we not know. Well, we know the initial velocity in the x direction is 20 meters per second, right? If we wanted to figure out t here, we'd need to know what delta x is. Well, the total time that's going to be in the air, it's going to traverse this distance in the x direction. Do we know what that is? Not yet. So that's not going to be helpful. That's the only thing that there is in the x direction, though. So that makes us come over here and look at motion in the y direction. We know that vy initial is equal to 0. The initial velocity in the y direction is 0. And then we ask ourselves, well, could we utilize that to figure out some other things? Well, if we go ahead and say this is equal to 0, if we knew what vy final is, we could figure out the total time, but we don't know what vy final is. How fast is it going when it reaches the ground? This doesn't really give us time at all, so let's look at this one here. We know what vy initial is. Time is what we're looking for. If we knew what its displacement was in the y direction, we could go ahead and figure out the time that it's in the air for. So the question is, do we have that information? And the answer is, yeah. By the time it reaches the ground, it goes from this elevation, 10 meters above ground level, to this elevation, 0 meters above ground level. What has it done? It's dropped 10 meters and reaching the ground. So we know that delta y is equal to y final minus y initial, which would be 0 minus 10. Ultimately, -10 meters is its displacement. -10 meters. Downward, that's why this is negative. So we've got those two pieces of information though, now. So what can we do with them? Well, again, we can go ahead and look at this expression right here and utilize it. So from this, we've got ourselves part A, this going on here, and we've got that delta y is equal to -1/2 g t squared plus vyi times t, where vy initial is equal to 0. We know what delta y is. We just solved this out for t, right? So we can go ahead and multiply both sides by -2, divide by g, take the square root to isolate this t here. We've got ourselves t is equal to the square root of 2 delta y divided by g. Square root of -2 delta y divided by g. So this is the square root of -2 times, well, delta y is -10 meters divided by g. Gives us time that is in the air being equal to square root of 20 divided by g. Square root of 20 divided by 9.8 gives us 1.42857. We'll call it 1.4286. That's what we'll say. 1.4286 seconds. We could round that out to 3 significant figures, call it 1.43, Now it'd be fine too for a final answer. I'm just keeping some significant figures there. No harm in that. So there's how long it's in the ground. Excuse me, there's how long it's in the air, how long it takes to reach the ground. What's interesting is that the x direction does not matter. This is basically just relying on free fall. An object that is dropped from rest has an initial velocity in the y direction equal to 0, right? How long does it take that object to fall to the ground from 10 meters above ground level? 1.4286 seconds. That's how long. It doesn't matter that this object was initially moving in the x direction. It takes the same amount of time to reach the ground because it has the same initial velocity in the y direction. That is to say that it is the initial velocity in the y direction and the displacement in the y direction itself that the object traverses, which ultimately dictate how long the object is in the air for. The displacement in the x direction's just along for the ride. As long as it's still in the air, it's still moving in the x direction. That's it. But how long it's actually in the air depends on these two pieces of information there. So I remember hearing this when I first took a physics class, much like this one, and it seemed unintuitive to me. It seemed like, nah, if you throw something really fast, it's in the air longer than if you just drop it. And I went home and I started throwing some rocks, trying to sink them out, trying to drop one and throw one simultaneously. The trick is you got to really make sure that you're throwing something completely horizontally initially and dropping them at the same time. But I did it enough. I did it enough to where I convinced myself that, hey, yeah, that's true. And if you think about it, why shouldn't it be like that? If there's nothing affecting its motion in the x direction, that's really just under free fall in terms of the y direction. Nothing else there to hold it up longer. That is, of course, assuming that we neglect air resistance. So, under that contingency, doesn't matter. Start putting air resistance in, and then you have, well, yeah, it kind of depends on how fast the object's moving and such things. But nonetheless, no air resistance, displacement in the x direction is linear with respect to time, and really has nothing to do with how long it's in the air for. Along for the ride, this is what it has to do. So, there we go. Let's figure out how long it takes to drop to the ground. All right, so there was a part A. We can go ahead and start asking ourselves some other things, like what is the total displacement in the x direction, or the displacement in the x direction when it reaches the ground. So we want to know what this delta x, we'll call it delta x max, maximum displacement in the x direction. B, delta x max is equal to what? Well, go over and look at our expressions that we have. We're dealing with the x direction now because we're asked specifically about delta x. Well, we've got an expression that says delta x is equal to vxi times t. So this is what it comes down to. If we know what its initial velocity is in the x direction, and we know the time interval over which we're considering its motion, we know how far it's moving in the x direction. In this particular case, we want the total distance it moves in the x direction by the time it reaches the ground. How long is it in the air for? Well, we just computed that. That's this right here. So this is, we could subscript this with a total if we want, the total time that it's in the air for. So we have that delta x max is equal to Vx initial times T total. And we know what T total is, 1.4286 seconds. And we know what Vx initial is. We've already determined that that is 20 meters per second. So if we use those two components, or those, the x component and the total time, and get ourselves the delta x max is going to be equal to 20 meters per second times 1.4286 seconds. Let's just pop that in here really quick. So times 2, we get about 2.8571. 2.8571. What do we have? Oops, sorry. This is incorrect. Incorrect, because I did times 2. That should be 28. Hold on. Yeah, 28.571. That's a good one. We just put in 2, didn't put in 20. 28.571 meters. There's how far it moves in the x direction. So if we think about how this is scaled, the little picture that we drew, it's wrong. Because we don't have that, well, if this is 10 meters, then this is 28, which is approximately really 30. So if we were trying to scale this out better and have a better pictorial representation, really, if this is 10 meters here, we'd say, well, there's 10, there's 20, and there's 30, so the object really goes in kind of a different way, kind of like that. But still, even though our picture wasn't completely correct, it still guides us in terms of what we're solving out, what we're looking at, and what sort of features and quantities we have. And then we can always redraw it to have a more realistic, or I shouldn't say realistic, but matching aspect regarding what's actually happening in that given problem. So, stretch farther away, down there. Oh, great. So, what can we do? Well, we could redraw that, but it'd be kind of messy. But you know what? I am, just because the next questions that we ask kind of have contingencies on that. So I'm going to erase that path right there. This is more like the path. And then let's just erase this stuff right here. Already got that written down. And try to put this back in. That was 10, 20, say 28, somewhere around like there. God. Something like that. So this is where it strikes the ground. All right, and then we call this delta x max now. 28.371571. So, yeah, 571. All right, next question. What is the total displacement of this object when it reaches the ground as a magnitude and a direction? Well, now we're asked something that correlates with where did it start and where did it end. Total displacement is just really a feature of that. So if we start right here, and we're ending right here, the displacement vector, total displacement vector, is a vector that points from where we start to where we end, right there. And what do we call it? We call it delta r hat. What does delta r hat have? It has a magnitude and a direction. The magnitude is this length in space, this distance in space, and the direction is some angle relative to the positive x direction. So, let us figure out what those are, right? So this is what we want to get. We got ourselves a part C now, and we got in general that delta r hat is equal to delta x I hat plus delta y j hat. Split things up into its separate components. And, well, we already know this, right? We know that this is going to be equal to 28.571 I hat. That's how far it moves in the x direction by the time it reaches the ground. And delta y, it's dropped 10 meters. So this is going to be 28.571 meters I hat minus 10 meters j hat. Displacement in the x direction upon reaching the ground, displacement in the y direction upon reaching the ground. What do we do from there? Well, what the magnitude and direction? The magnitude of delta r hat is the square root of the squares of the x and y components. So we've got this in general, delta x squared plus delta y quantity squared, which is then equal to the square root of 28.571 meters quantity squared plus negative 10 meters quantity squared. And we can get the straight line distance from where it began to where it ends as being squared as 30.271. 30.271 meters. So there's how far it moves in total in terms of where it starts to where it ends, total displacement vector. And then we've got the theta delta r is gotten by looking at the arctangent of the y component divided by the x component, delta y over delta x, which is then equal to the arctangent of a negative 10 divided by 28.571, which, making sure that we are in degrees here, we've got the arctangent of 0.571 divided by negative 10. Oops, excuse me. Arctangent of negative 10 divided by 28.571. And we've got about negative 19.29 degrees, negative 19.290 degrees. So in the end, we could write this out that delta r hat is equal to about 30.3, we could call it, 3 significant figures. I'll just call it 271 meters at negative 19.290 degrees. And think about it, does that make sense? It's nice to make sure that things make sense. And well, yeah, that's a little bit farther than just the displacement in the x direction. So that makes sense. The hypotenuse of that triangle should be bigger. And this angle here, well, that angle's not super large. It's a pretty acute angle there. Reasonable, 19, 20 degrees, sure. So, that's it. Now that's not to say that this object moved along that path, right? The displacement vector and the actual trajectory of this object, two very different things. That's just the straight line distance from where it started to where it ended, and the direction that it would have to move in to move along that straight line to get to where it ends. But we can still compute it. There it is. All right. Let us look at part C, part D. We are asked now, what is the velocity as a magnitude and direction of this object as it reaches the ground? So now we want to know, hey, how fast is this object moving and what direction is it moving in as an angle relative to the positive x direction when it reaches the ground? Ultimately, this object has some velocity vector right when it reaches the ground, just before it contacts the ground, or just as it's reaching the ground, that is tangent to the path that it makes, like that. There is some angle, theta sub v, and some magnitude that is the speed of the object as it reaches the ground. So let's figure out what that is, right? So as it reaches the ground, d, as it reaches the ground, v hat final, we'll call it, is equal to vx final I hat plus vy final j hat, keeping things in components. Well, we know that vx final is equal to vx initial, and vx initial is just 20 meters per second. So we've got this, vx final is equal to vx initial is equal to 20 meters per second. What about vy final? Well, we could figure that out. It's not zero, right? It's moving downward as it reaches the ground. And it's moving downward more and more as it gets closer and closer to the ground. So for vy final, we have to start looking at negative gt plus vy initial. That'd be one way to go about it. And what do we know? Well, t is equal to 1.4286. 1.4286 seconds. That was the time that it took the object to reach the ground. 1.4286, it's still up there. Anyways, what do we have? Well, vy initial was equal to 0, so we can solve for vy final. Vy final is then equal to negative g times 1.4286 seconds, which gives us 8 times 1.4286, negative 14.000. negative 14.000 meters per second. The negative says, hey, that's in the negative j hat direction, downward. That's the direction that it's moving at in terms of its y component as it reaches the ground. So what do we have in terms of the final velocity as a magnitude and direction? V final hat as a magnitude is equal to the square root of the sum of the squares of the x and y components, Vx final squared plus Vy final squared, which is then equal to Vx final, is still just 20 meters per second quantity squared, plus 14 meters per second quantity squared, giving us the speed with which it reaches the ground is 20 squared times 14 squared. 24.413. 24.413 meters per second. And we can get the angle, or the direction that it's traveling at. Theta sub V final is going to be the arctangent of Vy final divided by Vx final, which is the arctangent of negative 14 divided by 20, which gives us that our theta V final is equal to, go ahead and compute that out, arctangent, negative 14 divided by 20, negative 34.992, negative 34.992 degrees. There we go. That's how fast it's going when it reaches the ground. That is the direction that it's moving in relative to the positive x direction, which is negative angle below the horizontal. So that's what we've got. This doesn't really seem to match 35 degrees. This looks like quite a bit bigger, but some of that because I don't actually have the true trajectory drawn in. I have some approximation of it. I just kind of drew in some sort of arc there. We'll get to that later on. It's a whole different story. Anyways, we answer it. And really, any time for which the object is between this position and this position, we can figure out exactly where it is, how fast it's moving, and what direction it's moving in. Whereas total displacement, anything about the object, well, it's the projectile. Anything between t equals 0 and t equals 1.4286 seconds. Pretty cool indeed. All right, so one of the good points here, how long it's in the air for was dictated by its initial velocity in the y direction and the total displacement in the y direction. That's it. Everything else kind of falls into place from that. All right, we'll take a look at another problem here coming up, but this one's done for now.